Welcome to my lecture on discrete probability. We're going to be talking about discrete random variables and probability distributions, along with a whole bunch of other topics. Okay, so let's get started. So my first example of a discrete random variable is you could collect data, and X could be the number of cats in a randomly chosen individual, number of cats that they own. So not in, but by. This probably makes a little bit more sense. And notice that like X, it takes on numbers that are discrete. So like you could have 0, you could have 1, you could have 2, it could keep going. But this is called a discrete random variable because the outcome represents a whole integer. Okay, it could be either finite or infinite. Okay, and if we collected data, and this is fake data, on 10 individuals, you might have an individual with no cats, someone with 2, a whole bunch of individuals with 1 cat, another one with 2, someone with 3, a whole bunch of people without cats, and maybe someone with 1. Okay, so let's just pretend that this is our random sample of the number of cats owned, and notice like we always have an integer outcome, 1, 2, 3. They're called the counting numbers because we can't have half a cat. You don't have 1.5 cats, you don't have 2.3. X is always a whole number, okay? And that's the case with these discrete random variables, okay? Now what I can do is I can organize this data that's collected right here into a table, okay? And if I organize into a table, well, here's the outcome of X, right? And here's my data again. Okay, so the outcomes of X were 0, 1, 2, and 3. And 0 occurred with a frequency of 1, 2, 3 times, 1 occurred 4 times, 2 occurred twice, and 3 occurred once. So the total number was 10. And if I put this into probability, I just take 3 out of 10, 4 out of 10, 2 out of 10, and 1 out of 10. And that adds up to 100%. So that's always a check that you have a probability. Okay. So this right here, this is called a probability distribution of a discrete random variable X, where X is the number of cats owned by a randomly chosen individual. Okay. And we're going to be dealing, instead of having data in raw form, we're going to be dealing with data in tabular form. But I'm going to be discussing the relationship between the two in this lecture. Okay? When you have data in raw form like this, we talked about forming descriptive statistics in previous material. And one such descriptive statistic is just the average number of cats owned. So if I want to do that, I'll just take this data, add it all up, and divide by the total, which is 10. So I add up all this data, I divide by 10, and I get 1.1 cats as the average. Okay. So please, one thing that I'd like to remark is please do not round this 1.1 down to 1. That would be incorrect. Even though the outcome of X has to be a whole integer, the average and expected values can be decimals, okay? Now I'm going to rearrange this data. So I'm going to organize all the zeros. There are 3 of them, right? We see that by the frequency. Then there are 4 ones. I'm going to group them. I'm going to group the 2s, and I'm going to group the single 3. And they're all divided by 10, and I can regroup this to be 0 times the number of zeros, which is 3 over 10. That 3 out of 10 happens to be the probability, 0.3. Now I can group all the 4s, and this 4 out of 10 represents the probability, and 4 times 1 gives me these 4 ones. Now I can take these 2s, there happen to be 2 2s, so that's 2 times 2 out of 10, and 2 out of 10 represents the probability. And I can do 3 times 1 out of 10. This is called the expected value. It also represents the average. And in formula notation, the expected value is X times its corresponding probability, and add them all up. That's what this symbol here represents. So in your book, sometimes I think this is confusing notation, but E of x, the average or expected value of x, is nothing more than the average. Okay, and instead of dealing with data, you're going to be dealing with tables in this chapter. Okay. Let's continue on with this with our descriptive statistic. Another descriptive statistic that we talked about is variance. Okay. Now, variance is calculated as the expected of x squared minus the mean squared, or E of x. We already calculated the average or expected value, that's 1.1, so we square it. The only thing we need to do is calculate E of x squared. And E of x squared says square the value of x. So I'm going to take 0 from the x. I'm going to square 0. Multiply it by its probability. That's 0.3. And I'm going to take 1. I'm going to square it. Multiply by 0.4. The value of x is now 2. I'm going to square it. Multiply it by its corresponding probability. Then I'm going to do the same for 3, square 3, and multiply it by its probability. The expected value of x squared is 2.1. I can use that to calculate variance. Variance is E of x squared minus the average squared. That's 2.1 minus 1.1, and that's 0.89. The units of variance is the original unit squared, so that would be cats squared. And I don't know about you, but I haven't seen too many square cats. I've seen some fat cats, but I haven't seen squared cats. I guess they just need to kind of square them out. So if you want the units to have the original units of cats, or your original unit, you just take the square root. And that will be 0.943. So the variation is 0.943 cats, or nearly 1 cat. Okay. Now, this table right here, that's called a density table. And usually it just lists x versus probability. You don't get frequency. Okay. And here's a few properties that you should have noticed from this table. This table, all the probabilities are positive. Okay. And all the probabilities add up to 1. So there are 2 rules to be a valid density table. The sum of all the probabilities is 100%, and each probability has to be between 0 and 1. That's the only requirement. So let's review what we've covered thus far with another example. So here's a density table. The values of x take 1, 2, and 3. And we have probabilities, an unknown probability for x equals 1, plus probability x equals 3, plus probability, plus probability x equals 2 is 0.3, probability x equals 3 is a half. And here are some questions that I hope to answer. First question is, what is the probability of x equals 1? What is this unknown value? Second question is, what's the expected value? What's the variance? And what's the standard deviation? Well, let's answer this first question. What is P of x equals 1? Well, we're going to use this rule about probability tables. And so notice here you just have x versus P of x. You don't get to see the raw data, and you don't get to see the frequency. Okay, so you're left with dealing with just this table. And that's what most of this chapter is about, is just this table. So if I want to find probability x equals 1, we're going to use total probability as 100%. So 100% is equal to adding up all the probabilities. Add up probability x equals 1, x equals 2, and x equals 3. So this leaves us with 1 equal to the unknown probability plus 0.3 plus 0.4. And we can just subtract these two quantities from 1, move them over to the other side. And I apologize, that should be 0.5. That gives you probability x equals 1 is 0.2. So 0.3 plus 0.5 is 0.8. Subtract from 1 is 0.2. And that's our unknown probability. Okay. So we get this table at the end of the day. That's our density table once we solve for unknown probability. And I like to go back, like this question mark, it could have occurred anywhere here. It could have, I could have had 0.2 being given, and I could have not known that probability of x equals 2 was 0.3. I could ask you to solve for any of these probabilities in the table, but just one. Okay. So now if I want to find the average value of x, that's just called e of x. And I'm going to take 1, multiply it by 0.2. I'm going to take 2, multiply it by 0.3. I'm going to take 3 and multiply it by 0.5. And that's exactly what this is. This is x times its probability, adding them all up. That gives me 2.3. Okay? Now, if I want to find the variance, I need to know e of x squared. So that says square 1, multiply it by 0.2, square 2, multiply it by 0.3, square 3, multiply it by half. And that's what's done right here. I get 5.9. So now I can calculate variance. That's going to be 5.9 minus 2.3 squared. That's 0.63. And if I want standard deviation, because I want my original units, I take the square root, I get 0.78. Okay. Now, just a few things to discuss. Our probability took the form of a table. It can just as well take the form of a graph. Like I could graph this and make a bar chart of x versus its probability. And I can make a bar chart out of this table. Another thing that I can do is I can make a formula out of this table. Okay. Common things that you'll be asked to do with either a table, a graph, or a formula is to calculate the probability, the expected values, the variance, standard deviation from P of x. And P of x takes any of these forms. Now, the next distribution that I want to talk about is a very special probability distribution formula that only applies in certain situations, and that is the binomial distribution. So it has the form of a formula. And so now we're going to be dealing with formulas. Okay, but only in this specific situation. So don't misuse the binomial distribution. So here's the binomial distribution. And it requires all of these things. It says the experiment has a fixed number of trials, n. Okay? And a trial is an individual outcome, or repetition of the experiment. Okay? And each trial, the outcome of one trial doesn't affect the other, so it's independent. Each trial has either one of two possible outcomes. We usually call this success or failure. And the probability of success has to remain the same for each trial of the experiment. And the random variable x is the number of successes out of the n trials. Okay. If you have all of these requirements, then you can apply the binomial distribution. But if you do not have all of these requirements, you need to exercise caution and know how well your answer approximates the true probability, or if it's reasonable to apply. Okay. So if you have those situations satisfied, then probability of x is given by what's called n choose x times probability to the power of x times the probability of 1 minus p to the power of n minus x. Here, n is the number of trials, p is the probability of success, so 1 minus p is the complement, is the probability of failure. And n choose x is calculated with this formula. And you might be wondering why there are all those apostrophes. Are they just excited numbers? Well, the answer is yes, but it has more meaning than that. N factorial, or n apostrophe, means take n, multiply it by all the numbers until you hit 1. So, for example, 3 factorial is 3 times 2 times 1, that's 6. And that's how n choose x is calculated. A side note on n choose x is the number of ways of selecting x objects out of n. And that's what the formula represents. Okay. Now, a couple more properties about the binomial distribution is the average of x is just n times p. The standard deviation is the square root of n times p times 1 minus p. Okay, and you can use an online calculator. I have one linked here to calculate binomial probabilities. If you don't want to plug these numbers into your calculator, you can do it on a computer. That would be okay. Now here's an example of trying to solve a problem. So it says at a company producing parts that produces parts, okay, the probability the part is properly produced is 95%. And it says a shipment contains 25 parts, and if they just shovel the parts into the shipment, what are the odds that more than 2 parts are defective? Okay. So I'd like to point out here, the outcome of each part is independent. One part's outcome doesn't affect the other. We have a finite sample size or trial of 25 parts, and we have a probability p that's 95%, and this 95% is calculated by company records. They should be doing quality control on if their parts are defective or not. Okay. So we want to calculate the probability more than 2 parts are defective. So we calculate probability x is bigger than 2. And I'm going to do the complement because there's a lot of ways x could be bigger than 2. X could be 3, it could be 4, it could be 5, all the way up to 25. It's easier to do the complement. So the complement of x being bigger than 2 would be x being 2 itself, because that makes the statement false. X could be 1 or x could be 0. Okay, so these are the probabilities that I have to calculate, and I use that formula that I have listed, and I can see that there's a 1.1% chance that I produce more than 2 defective parts. Okay. Now, if I want to use an online calculator, there's one here. So remember, probability P is 95% for each individual trial. So this is a link to the online stats book, and it has a section here called calculators. So you can see here at the title is onlinestatsbook.com, and I'm going to go to the calculators. There's a binomial distribution one here. I'm going to click on that. My sample size here is going to be 25. That's the number of trials. My probability of this being of success is 0.95. And I want to calculate the probability that x probability is 0.05. Okay. So one thing that you should pay careful attention to is that the chance of each part being defective is a 5% chance, and x is the number of defectives. So I want to count the number of defectives. Probability of defective is 5%. So I almost got myself there, so you need to be extra careful. Probability of defective is 0.05. I have 25 parts. I want to know what are the odds that more than 2 are defective, and I calculate this as 0.127. So I have 0.11, they have a slightly different answer because of rounding, but this is reasonable. And so you can replace this with 1.2, or I used a different calculator and I got 1.1%. Okay. So I'm happy with this. This is 0.012 as my answer, having more than 2. Okay. And we can proceed to our next problem because we have solved this one. Okay. Probability of having more than 2 defectives is 1.1% chance. So we're pretty happy with those odds if we're the company. Okay. So here's another example, and this is one that we talked about before. It's the U.S. Supreme Court of Swain versus Alabama. You can read more about this. I encourage you to Google it if you want to read more about it. But it says in the 1960s in Alabama, Robert Swain was convicted of raping a white woman and was sentenced to death. He appealed his sentence, citing other factors, one of which was that there was an all-white jury, and he didn't believe that this provided him the rights that he was granted as a U.S. citizen to a fair trial. So at the time, only men aged 21 or older were allowed to serve in juries in the county, and the county was 26% of the eligible jurors were black, but there were only 8 black men among the 100 selected for the jury panel in Swain's trial. And for the final jury, so they form a jury panel, there's 100 people that could be jurors, and that's the jury panel. But in the jury itself, no black man was selected. Okay. The U.S. Supreme Court denied his appeal, saying in its ruling, the overall percentage disparity has been small and reflects no studied attempt to include or exclude a specified number of black Americans. The jury panels were supposed to be selected at random from the eligible population, so that's an important part. Because the 26% of the eligible population was black, only 8 men on a panel of 100 seems pretty low. Okay, so there's this thing called a struck jury, which is a part of selecting a jury from a pool. And first, potential jurors are eliminated for hardship. Second, jurors are eliminated for cause by conducting voir dire. Until there is a pool available that is at exactly the size of the final jury, okay, plus the number of premonitory challenges available to each side, and the two sides exercise their premonitory challenges on the remaining pool, usually altering. This procedure has its roots in ancient common law heritage. Through this process, several people have argued that it's not possible to get a fair trial, and that there's certain aspects of this that are unethical in similar cases that lack representation, or because the lawyers are simply trying to exclude individuals that would be more sympathetic to one cause or the other. And so this has quite a long history of eliminating individuals from being on a jury. Okay, and usually people will, in the past, in some sad instances, people have been eliminated because of their race, because they think they'll be more sympathetic and won't provide a fair trial. But it might also be misrepresenting not allowing for a fair trial or representation of the individuals. Okay, so anyway, here's our goal. Our goal is to assess the Supreme Court's statement: the overall percentage disparity has been small and reflects no studied attempt to include or exclude a specified number of black Americans. And I apologize for that. That was a direct quote. And so let's analyze this. we're going to use the binomial distribution to approximate this answer. And I want to emphasize this is an approximate answer. So here, there are a fixed number of trials. There's 100 possible individuals that could be selected. Okay. And either an individual serves, which will count as a success, or they're not selected for the jury, the trial jury, which we'll call a failure. So X is going to be the number of Black Americans selected out of 100 for jury panel. Okay. Here's going to be the assumptions that we need to assess to use the binomial distribution. We're going to assume each trial is independent. This means one individual's chances are not affected by another. This is likely a safe assumption, as we're supposed to have a random sample of the population. Okay. But it's not completely true. Okay. Just because there's a finite number of seats. Okay. The probability of selecting a Black individual from this population, an eligible one, is 26%, as was stated, and that's formed from the demographics of the county. Now, 26% is a relatively safe assumption, but every time you select one individual and their success, that changes the probability of the next person, but by a very small percentage, because there's a large enough population. Okay, so it might only change this 26% by a small amount, but it would typically decrease it by a little bit. So this will be an upper bound for our probability, but technically it should go down just by a teeny bit. But because there's so population, has more, like more than 100, like more than 1,000, this percentage is not going to change by much. Okay. So that's a fairly okay assumption, but it's still an assumption. Okay. And these are the two assumptions that are question marks for the binomial distribution. The others are okay. 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 Now, this is just noting that our assumptions, there are two assumptions that we have to make, and they could change our answer, but they're unlikely. So we're going to proceed with the binomial distribution, and we're going to compute the probability that 8 or fewer Black men are selected in the jury panel. Okay. So if I want to calculate that we see at most 8 Black individuals selected for trial jury, well, it's possible that X is 0, X is 1, all the way up to X is 8. And the final probability I get is 4 times 10 to the negative 6, which is essentially 0. Now, what I conclude from this is that if the rule of law was indeed followed for this court case, the odds of having 8 or fewer Black men selected for jury panel is essentially impossible statistically. And it means that they're likely violated. And that is the conclusion. Now, I'm going to show you how we calculate this probability, and I used a different calculator than the one I'm showing you. So let's go back to this online stats book. Our sample size is 100. That's how many trials there are. Either they're on the panel or they're not. This is 0.26. Okay. And we want it to be below 9, actually. And the reason why it's below 9 is because the first number that's less than 9 is 8, then it's 7, 6, 5, 4, 3, 2, 1, and then 0. And that'll be all of it. So below means not including 9. And we're going to recalculate. It gives me a probability of 0. Okay. And notice that this kind of forms a nice normal curve. We'll talk more about that later. But with a sufficiently large sample size and a probability here of 26%, the outcomes roughly form a normal distribution, which is rather interesting. Okay. All right. So that was all that I have for today's lecture on discrete probability distributions. The key things that I want you to take away is that you should be able to deal with probability distributions from a table, calculate their expected value, calculate their variance, their standard deviation, calculate probabilities with them, know when and how to apply a binomial distribution. And you really need to assess if you can use a binomial distribution. And that comes from looking at the assumptions of the binomial distribution. So the requirements, which are right here. Okay. All right. Well, thank you.